Alright guys, what's up? Welcome back. Gonna go over an example here with a current controlled voltage source, and basically we just want to figure out what the voltage drops across every element are and the power dissipation and delivery in each element, and then we can compare those to make sure that we have the right answer. So looking at this problem, we have the current controlled voltage source right here. This is a dependent power source, and it is basically 4.5 ohms times Ix. Now Ix is the current that's passing through this element. So first of all, we have to find the current passing through here. It's actually going to be really easy. And then we can find out what the voltage is that this is going to put out, and then we can go ahead using Ohm's law and KCL and KVL and whatever to basically come up with the solution to the problem. So let's get started. Don't be alarmed when you see something looking like this. It's actually not too bad. This unit here of ohms just has to be here for the calculation to make sense. So when we look down here at the independent current source, it's 2 amps. Basically, it's going to force 2 amps of current through this branch no matter what. And it will use any amount of voltage required for that to happen. So that means there's 2 amps flowing like this. So we can label that on at this junction right away. So we have 2 amps. And then we also know that there's going to be 2 amps coming in like this. So coming out of that junction, we also have 2 amps, which means that Ix is equal to 2 amps. So that just makes this really simple. We have 4.5 ohms times Ix, so times 2 amps. And because of Ohm's law, V equals IR, basically ohms times amps gives us the units of volts. So 4.5 times 2 just gives us 9 volts. Okay, so the next thing that we want to do is, I always like to try to apply Ohm's law everywhere I can on all of the resistors, just in case there's something that's available for us. And here, in this case, it's going to be this resistor that we can solve right now. So if we just write the expression here for V equals IR, the current here is 2 amps times the resistance of 1 ohm. So we're just going to find the voltage drop across this resistor to be 2 volts. But if you want to look at the other resistor, like this one or this one, we actually don't know what the current is right now flowing through this branch or flowing through this branch in between the 2 loops. And so basically the easiest way to figure this out is to use mesh analysis. And I will make some videos on mesh analysis, and when they're done, I'll put a link in the top right corner. If you're watching this video around the time that it gets posted, I haven't done them yet, but if you're watching in the future, then the link should be there. But basically what you do is you identify the current flowing through each loop. So we have a loop on the top. We're going to call that current going clockwise I1, and we're going to call this current here on the bottom loop I2. And the convention basically is to just assume that there's a clockwise current going around each loop. That means that from this one, the current that's coming from this loop is going to go clockwise through this element that they share, and this current is going to go the other way through the element that they share. And so the actual current that's flowing through this is the sum of I1 going this way and I2 going this way. And then all we do is we just apply KVL around each loop, and we just use that condition, and you'll see here that it's going to work out really easily for us. So let's write KVL for the first loop. Let's call it loop number 1. And let's maybe label on our polarities here just so it's going to be super clear. So this is going to be negative to positive, and then when we come into the resistor, it will be positive, negative, and then we're going to assume that the current's going this way, positive, negative. And then here we know this one has to be positive and negative like that. And then the independent power source is going to be negative and positive. Okay, so when we write KVL, we're basically just going to sum up the voltage drops as we go around. So let's just start here and go around the loop and come back to this node. So when we enter in the dependent power source, it's going to be 9 volts, negative 9 volts. And then because we have the expression for Ohm's law, V equals IR, we can just apply what we know for the current and the resistance in place of the voltage. So for this resistor here, the voltage is equal to the resistance times the current. So we just have that being plus 3 ohms times this unknown current, I1. And then for the next resistor, the voltage is also just equal to the resistance times the current. So we have plus 2 ohms, and it's that times the net of the current. So it's going to be I1 minus I2. Like we said, I1 is going this way, and I2 is going this way, but we've defined the current to be going this way. So the net is I1 minus I2. Okay, and then we just set all of that equal to 0. Now let's also write KVL around loop 2. And we can actually just skip all of the work because we already know that I2 is going clockwise, but we know that there's a real current of 2 amps going counterclockwise, so I2 is just going to be equal to negative 2 amps because they're just pointing in opposite directions. So let's just write this here as I2 is equal to negative 2 amps. Now what we can do is we can plug this back into our expression in KVL of loop 1. So we get minus negative 2 amps, and let's actually just change that to be plus 2 amps. And set that to 0. And then we can just distribute the 2 ohms throughout the brackets. And this ohms times amps just becomes volts. So that's plus 4 volts. So we have negative 9 volts plus 4 volts, so that is negative 5 volts. And then we have plus 5 ohms times I1 is all equal to 0. So when we rearrange for I1, we just get that's equal to positive 5 volts over 5 ohms, and we find that I1 is equal to 1 amp. So that's basically saying that the current flowing around this part is equal to 1 amp. So we can label that on coming into this junction here as 1 amp, coming out of this junction as 1 amp. And you can look at this side, if we have 1 coming in and 2 coming in, there has to be 3 going out. So we have 3 amps, and then same here, we have 3 amps coming in and 3 amps going out. So at this point it would be also good to draw a ground. If you don't know where to draw it, you can just pick somewhere, and if you get negative voltages, I would recommend like just drawing it somewhere else until you only get positive voltages. So I already know that it's going to be here, but if you put it in the wrong place, it's okay, you could experiment a little bit. We're basically just going to define this node as 0 volts. And we already found the voltage drop across this resistor to be 2 volts, so we know that everything up here is 2 volts higher than ground. So we can just label a little thing up here for 2 volts. And then we know that this jumps 9 volts across this dependent power source, and so we're going to be at 2 plus 9 for 11 volts, basically above ground for this node. And then if we want the voltage drop across this resistor, because we also need to still find out what the voltage is at this node, we can just also do Ohm's law, so V equals IR. The current is 1, the resistance is 3, so the voltage is equal to 1 times 3, so this is a drop of 3 volts. So we're going to go from 11 volts down to 8 volts here. So this node has a voltage that is 8 volts higher than ground. Okay, so now we have the voltage at each node, and let's just make sure we know the drop across everything. So in the bottom left, the resistor here, the voltage drop is 2 volts. So maybe let's just put a little circle around this. This is 2 volts. The dependent power source here is 9 volts. This node here is 2 volts higher than ground, and this node over here is 8 volts higher than ground, so that means the drop across this resistor is 6 volts. Let's just label that on, 6 volts. And then the voltage drop across this one we found to be 3 volts. So let's put a 3 volt here. And then here, again, we're 8 volts higher than 0 volts, so the drop across this guy is 8 volts. So it's looking good right now. We found all of the node voltages. We found the voltage drop across every element. One good thing to do now, if you have the time or if you're asked to do it, is find the power dissipation and power delivered of each circuit element. So let's do the power dissipation of the resistors first, and we're going to use the expression P equals VI to find out what the power dissipation is. Let's start with the 1 ohm resistor here. So the voltage is 2 volts. And we just multiply that by the current, which is 2 amps. And we find the power dissipation here to be 4 watts. We can also do P equals VI for this resistor here. So the voltage drop is 6 volts times the current of 3 amps. That gives us 18 watts of power dissipation. And then for the other resistor up here in the top right corner, we have 3 volts times 1 amp. Which gives us 3 watts. And if you take the sum of all of those, we're going to see that we have a total of positive 25 watts, and that is the total power dissipation from the circuit due to the resistors. So we also want to check the power delivery into the circuit, so let's maybe just switch colors here, and we're going to also do P equals VI. And let's check the dependent power source first. So we'll also use the voltage, which is 9 volts, times the current, which is 1 amp. So we have 9 volts times, and we write this as a negative 1 amp. And that's because the current is flowing into the negative terminal. It's opposite to resistors where the current flows into the positive terminal, and we consider it a positive here. But that's basically just going to equal negative 9 watts. And when we do this for the independent current source down here, we're also going to do P is equal to VI, and we have 8 volts times negative 2 amps, so that's equal to negative 16 watts. And when we take the sum of that, we just find that we have negative 25 watts. So we have a total of 25 watts being delivered into the circuit and a total of 25 watts being dissipated from the circuit. And this nets out to 0, which is what we expect. So this is just a good check to make sure that we've done everything correctly. Or like I said, if you're asked to solve it, then yeah, this is how you do it as well, or one of the ways that you can do it. So yeah, I think that's the last video for dependent power sources. At first they look a little dodgy here because they have a whole bunch of symbols and things, but basically once you figure out the controlling voltage or the controlling current in this case, then you can treat these problems just like any other problem that has multiple power sources, and then we can use methods like KCL, KVL, Ohm's law, and also, as we've seen in this video, mesh analysis, and also nodal analysis. So yeah, that's going to take us into those next sections anyways, which will be on nodal analysis and mesh analysis. So thank you for watching, and I will see you guys there.